Hey there everyone, welcome back. We are starting a new unit today. Today's unit is on fluids, and we're going to study fluids in a static and a dynamic sense. So what happens when they're staying in one place, and what happens when they move around because there's forces exerted on them and that sort of thing. The first thing we need to do is define what is a fluid. And so maybe a simple way to state that is a fluid is a substance that can flow. And while that might not be a super technical definition, I think it captures the main idea here. That if I were to put this fluid into a container, it would take the shape of that vessel. And this is going to include both liquids and gases. There's an important difference between those two things, obviously. Well, there's a few differences. But for our purposes, the big difference between liquids and gases is that gases can be compressed. And what we mean by that is because there are space between the gas particles when they're moving around, if you exert a pressure on that gas, it is going to occupy a smaller volume. And if you reduce the pressure on that gas, it is going to expand out to fill that volume. So gases are fluids, but they're fluids that are going to occupy whatever amount of volume you give to it. Liquids are different. So liquids are what we call incompressible. Now, I should say they're largely incompressible. You can compress them a tiny, tiny amount, but it's so small that for our purposes, we assume that you cannot. And this is simply because the particles inside a liquid are already packed very, very close together. So while they're able to move and flow past one another and change shape of the overall substance, we can't really push those particles any closer together than they already are. And so when we describe fluid motion and all this, we're going to talk about incompressible fluids, which means we're largely going to be talking about liquids. One of the things that we're going to talk about when it comes to fluids is the density of the fluid. So the density of the fluid we're going to define as rho is equal to m over v, and that's capital V because that is volume. So for density, right here, we use the symbol rho. And we are going to measure that in kilograms per meter cubed. Now in other classes like chemistry, you might measure it in grams per centimeter cubed or milliliter or something like that. But in physics, our base unit is going to be kilograms per meter squared, which tells us, of course, that then the m here is our mass in kilograms, and this v right here is our volume. Now, it's important to notice that density is a useful property of matter because if you have a type of sample, say a bar of gold, while you might not know the mass or the volume, all gold has the same density. So if you have a very large gold bar, it might have a very large mass, or if you have a tiny speck, it might have a small mass, but either way, it's going to have the same density. And so this allows us to predict certain behaviors. Like, for example, if you ask somebody, is something going to float? They might ask you the question, well, is it heavy or not? But that's not really the right question because some heavy things do float and some light things sink. If you throw a pebble in the water, it definitely sinks. But you throw an entire tree in the water, then that's going to float. And the tree is clearly heavier than the pebble. But what the difference is the tree has a lower density. Since the tree has a lower density than water, it floats on water. And the pebble, even though it's very small and very light, has a higher density than water, and so it's going to sink. And this is one of the ideas of buoyancy that we're going to get to in the future video. So when we look at the density of different materials, and you're never expected to memorize this stuff, but we'll just use a couple of these numbers for our calculations here in a second, you can see they vary. Gases like air have a density around like 1 kilogram per cubic meter, 1.2, whereas water is like 1,000 kilograms per cubic meter, right? So what is the mass of air in a living room with the dimensions of 4 by 6 by 2.5? So density is equal to mass divided by volume, which means mass is equal to density times volume, which in this case is going to be density times length times width times height, because that's how we find the volume of a rectangular prism, or if that's what the room is. So this is going to be, we'll assume it's 20 degrees, so air is about 1.2 for our density times 4 times 6 times 2.5, which gives me an overall mass of air of about 72 kilograms, which I don't know, that's kind of maybe surprising. I never thought about how much air is in a room, but 72 kilograms worth. Here's a slightly trickier question. If you had the sun, so you have our entire sun, has a mass of about 2 times 10 to the 30 kilograms, quite a bit, and has a radius of 7 times 10 to the 8 meters, what would its new radius be if it collapsed into a neutron star? So some stars, when they die, collapse down into a neutron star. And just for the simplicity's sake in this case, let's assume that all the mass of the sun collapses so that it has the same density of a neutron star, which definitely doesn't happen in neutron star formation, but we're just getting started. So, well, one way to do this is we could figure this out in terms of ratios. We could figure it out proportionally. So I could say like the density of the sun to the neutron star, the ratio of the density of the sun to the neutron star is going to equal the mass of the sun divided by the volume of the sun over the mass of the neutron star divided by the volume of the neutron star. Now recognize that these two masses are going to be the same because they're going to stay constant, and so this whole thing would just equal the volume of the neutron star divided by the volume of the sun, because I'm dealing with those reciprocals. So the volume of the neutron star, which I'm going to assume is a perfect sphere, is going to be 4/3 pi r cubed, and that's the radius of the neutron star. And I divide that by 4/3 pi r cubed of the sun. So one of the advantages of doing this thing proportionately is you can see a bunch of these things are going to cancel out. So the 4/3 and the pi are all gone away, and I end up with a statement of the density of the sun to the density of the neutron star is going to equal the cube of the neutron star's radius over the cube of the sun's radius. And I'm getting a little bit squished for space, but we shall persevere. So we're looking for the radius of the neutron star. So if I solve this algebraically, I get the radius of the neutron star is going to equal the cube root of the density of the sun over the density of the neutron star times the radius of the sun. And so when I plug in my values here, I've got the density of the sun is about 1410. The density of the neutron star is massive, 6 times 10 to the 17. And the radius of the sun is, I had this up here, 7 times 10 to the 8. So plugging all that into your calculator, you should end up something in the neighborhood of about 9,300 meters, which is really, really small, which is why neutron stars are, well, they're big, but they're not as big as suns, and they're ridiculously dense. So, in addition to talking about density, when we deal with fluids, the other idea that we're going to just come back to constantly is pressure, okay? So pressure we define as the amount of force per unit area. So if I want to put that into a formula, you can already picture it here. The pressure is going to equal force over area. Now this is important to notice that this is P as in pressure and not rho as in density, and I apologize, but we keep picking letters that are easy to mix up, but that very much is pressure right there, whereas this is force and that is area. Okay, now the units for pressure typically, or at least the base units we're going to use are pascals. Okay, which is just capital PA for our abbreviation. So a pascal would be the same as 1 Newton per meter squared. And the average sea level, or air pressure I should say, at sea level, so we sometimes define that as 1 atmosphere, and you might see that in like chemistry or, well, physics courses. 1 atmosphere is 1.01 times 10 to the 5 pascals, which is like 101 kilopascals. So that's just kind of a useful number to have in your mind. So when we're thinking about pressure, it is related to force, but it is a little bit different. So something you might have seen, like a trick magicians sometimes do, is they have a bed of nails and they lie down on the bed of nails. Now, of course, if the magician were to just sit on one nail, well, then that magician would be stuck on a nail. But because there are so many nails, they kind of spread their weight over all of the nails, and overall the pressure isn't enough for it to break their skin. So if a magician lies down a bed of nails, suppose they have a mass of 70 kilograms, and each individual nail has a very small surface area of only 1 square millimeter, which is very small. How many nails would it take for them to lie down on safely if we assume that overall it takes about 70,000 pascals to pierce the skin? So we'll start off with our fancy new formula here. So pressure equals force over area. And one thing we could figure out is we could figure out the area. So the total area, and keep in mind this is like the total area required of all the nails, is going to equal the force divided by the pressure. Now in this case the force that's pushing down on the nails would be equal to the weight. So this would be the weight Fg, which is just equal to mg divided by the pressure. So 70 kilograms times 9.8 divided by a total pressure of 70,000 pascals. So this means we need a total surface area of 0.0098 square meters, which doesn't actually sound like a whole lot, but keep in mind this is square meters. So if I have 1 square millimeter, which is how big one of the nails is, I can convert that into square meters by multiplying it by 1 meter over 1,000 millimeters. But I have to recognize that because this is squared, then I have to square this whole thing in order for these units to properly cancel out, which means I'm not just dividing by 1,000, I'm actually dividing by 1,000,000, which means 1 square millimeter is actually 1 times 10 to the negative 6 square meters, which is very, very small. So I need a total area of 0.098 square meters, and each of my individual nails is only 1/1,000,000th of a square meter. So I might come up with a formula something like this, that the total area is just going to equal like the number of nails times the area of one nail, which is like, I guess, a formula. So the number of nails would just be the total area required divided by the area of one nail, which is 0.0098 divided by 1 times 10 to the 6. Negative 6, pardon me. And so you can see that we're going to need about 9,800 nails, or almost 10,000 nails, for that to be safe for the magician. Okay, so that's pressure quickly, but we want to talk about hydrostatic pressure. So hydrostatic pressure is kind of right in the name. Hydro, fluid, static meaning not moving. If you have a fluid that's just sitting there, anything that's submerged under that fluid is going to experience pressure because of what's weighing down on it. You've lived your whole life at near sea level anyways, and so you've experienced air pressure. And if you were to go up a mountain, your ears might pop because that pressure is changing, it's reducing just a little bit. So when we talk about hydrostatic pressure, one way to envision this is to picture like I've got a column of water. So maybe I've got like a glass of water, and in that glass of water, at the somewhere maybe near the bottom of the glass of water, I've got a fish. Now I'm going to draw a box fish because I can't draw fish, but I can draw a box fish. Okay. There you go. There's my little box fish. Happy little guy. Okay, so this is sitting in the fluid, and so this is going to experience a pressure. You can imagine if you were down at the bottom of a swimming pool, you would feel that pressure on top of you. Now, why does that pressure exist? That pressure is there because there's a whole column of this fluid, of this water, that's like weighing down on top of you. So this whole column here of fluid, it has weight. And that weight is weighing down on you, and it's exerting a pressure on you because you have a surface area. So that weight is pushing down on you. And so we need to have a way to kind of calculate this hydrostatic pressure. So we recognize that pressure is just force divided by area. Okay. Now let's keep in mind here that the force that's being pushed down on my little box fish is really the weight of the water that is on top of them. So I'm just going to call this Fw because that is for the weight of the water, okay, pushing down on top of them. And so this is really just going to equal mg over A. Okay. Now, it's important to note that the mass here is the mass of the water, not the mass of the fish. The fish's mass wouldn't have anything to do with the pressure. Now, I've got another formula that I learned before, which is density is equal to mass divided by volume. And so I could rework this equation here. I could rewrite this to say that mass is equal to density times volume. But let's think about what we mean by volume. So I'm talking about this column of air. This column of water that's sitting on top of the boxfish. Well, the volume of that column, column on top of the fish, would be equal to the height of the column multiplied by the area of the column on top. Okay, so I'm going to rewrite this here. So I've got mass. Mass is going to be equal to the density of the water multiplied by the area times the height. Okay. And so what we notice is I can actually take this whole thing right here and I can bring it along up here and I can sub it in to my equation up at the top. And so what I end up with is the pressure is equal to the density times the area times the height times g, all divided by the area. And a funny thing happens here, which is my areas cancel out. And so, long story short, this whole equation simplifies to be the pressure is equal to rho g h. Now, we need to be clear about a couple things here. This pressure is being caused by the fluid. So the rho in this example, we don't want to mix this up. The rho in this example is the density of the fluid. And the height really is the depth. It's not how tall the fish is or anything like that. In this case, h is how deep underwater it goes. And this sort of makes intuitive sense that the deeper underwater you go, the more pressure you should be feeling. Okay. Now, most things, like most fish that we deal with, are going to be on the surface of the earth. And so, because we're talking about the surface of the earth, there is this additional air pressure that sits on top of everything. So while you're under the pool, you're not only under a column of water, you're under a column of gas that extends way up into the atmosphere. And so the total pressure here is going to equal P naught plus rho GH, where P naught is basically our air pressure. Okay, so the total pressure you experience is the air pressure at sea level plus the pressure caused by being under that fluid. So if we want to calculate, for example, a submarine, we want to know what pressure it's operating under, and they want the answer in both pascals and atmospheres. We know that the total pressure is going to be P naught plus rho GH, which, as we saw before, was like 101 kilopascals, so times 10 to the 5, plus the density of water. And from the previous page here, you can jump back and see salt water has a density of about 1030 or 1030, so 1030, and then G is of course 9.8, and then our depth in this case is 300 meters. So this whole thing works out to be about 3.1 times 10 to the 6 pascals. Now, the question also asks for that in atmospheres, so just a reminder of our conversion factor. If I have 3.1 times 10 to the 6 pascals, there's 1 atmosphere for every 1.01 times 10 to the 5 pascals. Remember that 1 atmosphere is just the pressure at sea level, normal air pressure. So this works out to be about 31 atmospheres. Okay, and there's my 2 answers. Okay, so suppose that Superman is drinking from a very long straw. And that because he's Superman, he can create like a perfect vacuum in his lungs, right? He creates like a vacuum where there's 0 pressure in his lungs, and that causes the liquid to come up. So if I have a straw, and what's happening is there's some liquid that is filling the straw going up to a certain height. In actual fact, at first glance it might seem like that should be able to go like an infinite distance, that Superman could have a straw however long he wants and he should be able to drink from the top. But recognize that the pressure that's here at the top of the straw might be 0 because he's exerting like a perfect vacuum. But the pressure at the bottom of the straw is going to be equal to the air pressure outside. Essentially, what happens when you drink from a straw is you create a low pressure area at the top of the straw, and then the air pressure outside pushes the fluid down, which causes it to rise up the straw. You don't actually suck fluid up through a straw. In actual fact, you allow the air around you to push the fluid up the straw for you. So, in order to find the height that it could rise up, the pressure difference would have to be equal to rho GH, and that's our pressure that we saw before. So I'm going to assume that Superman is drinking water because he likes to stay fit. So in this case, the height that he could drink from would be the pressure divided by rho g, which is 1.01 times 10 to the 5 pascals divided by 1,000 times 9.8. Okay, so this ends up being about 10.3 meters, which, if we're being honest, is a very, very long straw, but still not infinitely long. There is a limit even for Superman. Okay, last thing we kind of want to talk about here is Pascal's principles. So Pascal proposed the following, that if you change the pressure in a fluid, at any point in that fluid, it will experience an equal pressure change across that fluid. So a pressure change in a fluid is experienced everywhere. In the fluid. So one great example of this is a piston, or like a hydraulic jack. Okay, so you can see here that we want to lift the car in the air, and so by doing that we exert a force on one end right over here, so that it exerts another force on the car to lift it in the air. Now the key difference here is that the two pistons, A and B, are different sizes. They have different areas. So when I exert a force on the one side, the pressure felt on the other side is the same. So essentially what we're saying is that the pressure felt at piston A is going to be the same as the pressure experienced at piston B, because the pressure is transferred equally across. Now, what does that mean about the forces? Well, that means that the force at A divided by the area of piston A is going to equal the force at B divided by the area of piston B. Now this sets up something that's a little bit counterintuitive, because what this means is that since the surface area of piston A is much smaller than the surface area of piston B, then the force at piston A will also be much smaller than the force at piston B. So the force on the large piston is much larger. And it's larger by a factor of the ratio of the areas. Now that's a little bit counterintuitive, but what we need to recognize, like at first glance, that seems to maybe break like conservation of energy. But what we recognize is, let's just trace what happens with, like, let's take a little slug of water, and a slug is like a little section of the fluid. Imagine that I compress piston A down so that I move this little red chunk of fluid here. Well, when it transfers over to the other side, it's going to correspond to something like this. It's the same volume of fluid because it's not compressible, but because it's spread out over a larger piston, it's going to correspond to a much smaller height. So even though we can exert a larger force on the car, the narrow piston must move more than the wide one, because the volume of fluid displaced by the two pistons must be equal. So the volume must stay the same, because we're dealing with a non-compressible fluid. Now this should remind you a little bit of a lever. It's a little bit like a lever arm, where you can use a lever to use a small force to generate a larger force on the other side of the lever, but the small force has to move that side of the lever a much larger distance to accomplish this. So imagine we've got a barber raising his customer's chair by applying a force. So if you've ever been one of those fun barber chairs, they step down on a pedal and they can lift you in the air, even though they're not really exerting a lot of force when they do that. So they push down with a force of 150 newtons, and the radius of the piston they push down on has a radius of r. And the piston of the chair you're sitting in has a radius that's 4 times larger, so 4r. This just also intuitively makes sense because they have to pump several times on the chair, and you're only really raising up small amounts each time. So how heavy of a customer could this person lift? So we know that, like, the pressure at the first point is equal to the pressure at the second, which means that F1 over A1 is equal to F2 over A2. So how heavy a customer, that would be the weight of the customer, and that would be equal to F2. So F2 is really just going to equal the ratio of the areas, A2 over A1 times F1. Now remember the areas, I'm going to assume that these pistons are circular, which I think is a pretty good assumption. So the area is going to be pi r squared divided by pi r1 squared times the force exerted on 1. And notice that the pi's are going to cancel out. Now the radii are 4 times greater, so I've got like 4r squared over r squared times F1. And again, now my r squareds cancel out, but I need to recognize that that 4 gets squared. So this is going to be 16 times more force, F1, which is equal to 16 times 150, which gives me a total force of about 2,400 newtons, which would be a fairly large amount of force. Okay, last question here to think about, and this is something just sort of conceptual. In each of these, I've got these kind of underground caverns, and they're all different shapes. And so which one of these, at the bottom of each of these, say the floor of each of these weird shaped pools would experience a pressure because of the water sitting on top of it. So which one is going to experience the greatest amount of pressure? And I think you might know the answer, and I think it might also be counterintuitive that the answer is none of them. That all points are the same. And that's because for each of them, the height that they are, the height of the fluid on top is the same in each case. And that's really counterintuitive. Like for me personally, I really kind of wonder about D, where there's all this water on top and then it narrows down to a point. And the key is that doesn't really matter, because all that matters with hydrostatic pressure is not the total amount of water on top, but just the actual height of water on top, and that's it. Okay, that is it for our first lesson on fluids.